Hello, my name is Dr. Catherine Crispin. I'm going to talk to you about an introduction to EDS analysis. Here at Penn State, we have multiple systems that have EDS detectors on them. 4 of them have an Oxford EDS system. The Barrios, Aprio, and eSIMs all have the Oxford system on them, as does the Helios FIB. We also have a Thermo EDS system on the Sios FIB. There are multiple instruments that can detect EDS for you on all of our different imaging systems. How does this work? Well, when your electron beam hits the surface of your sample, it generates a whole bunch of different things. It'll generate secondary electrons, which come from fairly near the surface, and this is what allows you to image in secondary mode. It also generates backscattered electrons. This is what can help you determine your phase differences because it's sensitive to the atomic number. But it's also going to generate a whole bunch of other things like the photoluminescence and Auger electrons from the surface. But what we are really interested in today is the characteristic X-rays that come off. And this is where it goes to the EDS detector to tell you what your sample composition is. The excitation volume is how deep it's coming from. So it's not just the surface of your sample. You're actually doing a bulk measurement. How do these characteristic X-rays get produced? Well, as the electrons from the beam come in, they will hit the atoms that are in your sample and knock off an electron from an inner shell. When this electron is knocked off, the atoms do not like to have a vacancy in an inner shell. In order to fix this, it will drop an electron from an outer shell down into that gap. But to do so, it must shed energy, and it sheds it in the form of the characteristic X-ray. So EDS, or energy dispersive spectroscopy, is when these characteristic X-rays hit a large area detector that then collates that into a histogram of X-rays. And it basically counts against energy. So it all maps out to the exact energy of the beam that is causing this to be knocked off. Almost all electron beam instruments today can accommodate one of these detectors, so they're extremely common and extremely well used. Almost all of them are now silicon drift detectors. What EDS is primarily used for is what is it? So what is your sample made of? It's also used qualitatively for where is it? So if you're looking for a specific phase, it can help you detect where that phase is. If you wanted to do quantitative analysis, you want to know specific stoichiometry, specific weight percent or atomic percent of what's in your sample, you have to use standards, you have to normalize the beam. That's when you compare a known standard composition versus your unknown sample in order to determine the correct breakdown. Briefly, silicon drift detectors are what makes this work today in a very rapid fashion. It's when the X-rays will pass through this isolation window. In our case, we use beryllium, and it will ionize. And then it goes through a bunch of different rings in order to get to the anode in the center. That converts it into a pulse output, and then it gets sorted in the multi-channel analyzer, and it gives you your histogram or your EDS spectrum. Your expectations for EDS analysis, EDS, the energy resolution is approximately 130 eV, so it's not as narrow as you might think, but fairly good resolution. You can detect somewhere between 1,000 and 3,000 ppm, depending on the element. You can see anything from beryllium and higher. Light elements is going to be really tough. High Z is where the best accuracy is. Your best accuracy, if you have a polished sample with standards, you can get accuracy of plus or minus 1%. That's not too bad. Agreement between these samples, if you do multiple samples, you can get some precision down to about 0.1%. This is what a sample EDS spectrum will look like. There is a histogram showing the energy on the x-axis and your counts per second per EV on your y-axis. It separates them out into peaks, and the software will then read these peaks and tell you what these peaks are. So in this case, you can see that it's identified each of these peaks, so you know what's in your sample. You can also do mapping. This is another very useful tool where you could actually use the mapping feature in order to find out where your different phases are. So it will collect data for you, and you can see some various locations for high elemental concentration for certain elements. In this case, these really bright regions are high concentration of magnesium. In this area where it's black, there's nothing of that particular element. That's silicon in this case. And anyway, you can just look and see how it all maps out to determine where your areas of interest are in your sample. We also have the ability to do large area mapping. And that's where you take individual maps all across your sample and then stitches them together afterwards. So you can map an entire, several centimeter sample and potentially, and stitch it all together to get a really good EDS map of your entire sample. There is one caveat. In EDS, the biggest problem that I see with users is that there are a lot of peak overlaps. The big spectra on the bottom, you can see that there's a huge overlap between germanium, arsenic, and selenium. It's almost impossible for the EDS detector to separate these peaks out because it uses a Gaussian fitting algorithm in order to fit these peaks and determine what the composition is in the amount there. The other common peak overlaps that I see a lot of is manganese chromium, titanium barium, which is a really rough one for people that are doing stuff with both titanium and barium in their samples. Silicon molybdenum also is a big overlap. So you have to be concerned when you're looking at your spectra and be aware that there could be peak overlaps that can influence your results. In summary, EDS is really good for a quick qualitative idea of your material. What do you have? It's very good for locating regions of interest, such as phases. It's very good for a rough estimate of composition. Not precise, but rough. If you want the exact stoichiometry composition, you really do need standards. There are a whole lot of caveats in addition to peak overlaps in order to understand your EDS data. I recommend that you check with staff if there are any uncertainties, such as the ones listed below, like peak overlaps, your sample's charging, it's non-flat, you're getting a lot of weird peaks that don't seem to match up. Come see one of the staff, and we can help you with it. Thank you very much.